Welcome to Everything STEAM. I'm your host, Sam Stanford. As a physicist and structural engineer with Jacobs Engineering, I've made many connections with some bright individuals who are either working, studying, or self-taught and passionate about our particular topic of discussion. So I hope you're excited about space and physics, because this episode is all about astrophysics. You'll get a look into cosmology, the sequence of our universe, what happens to galaxies over time, black holes, and their influences on galaxies. Then we'll shift gears and talk about a substance that is roughly 5 times more abundant than the matter that makes up you and I. To end this podcast, we'll give your brain a little bit of a break where we'll discuss education and science communication. And when I say we, I'm definitely not doing this alone. So I brought in someone who really knows their stuff about astrophysics. So please meet Skylar Grayson. Skylar is currently pursuing a PhD in astrophysics at Arizona State University. Her research focuses on galactic evolution using computational methods to model the universe and understanding how supermassive black holes led to a loss of material over time. With a diverse research background, including pharmaceutical lab work, dark matter research, and nanomaterial modeling, she has always loved the process of doing science. But it was astrophysics that captured her imagination more than any other field. On top of that, at ASU, she is working on a secondary project in education research and is passionate about teaching and inspiring the next generation of young scientists. This passion, of course, led her to social media, where she started posting videos on TikTok this year, sharing astronomy fun facts, and generally using it as a creative outlet. And as her platform grew, she expanded her reach in the realm of science communication to Twitter and YouTube, and has recently been accepted to participate in the NASA social event for the Artemis 1 launch. How exciting. So, now that you've been introduced to my friend Skylar, we're going to get right into the thick of things by discussing galactic evolution. Enjoy. Welcome to the podcast, Skylar.
Thank you for having me.
Yeah, this is great. This is a great topic. It's not something that I'm really in depth familiar with, but something that I just really enjoy talking about. Being that I have just such a small physics background compared to you, but we're going to be talking about galactic evolution. It kind of I labeled this as Galactic Evolution 101, so it's an appropriate
awesome
topic.
Yeah.
But the first question I have for you, and this is really cool. You were invited to a NASA social event for the Artemis 1 launch, and that's coming up in a couple weeks.
Knock on wood, yes.
Oh, how did that happen? How did that go down?
Well, so these social events are something that you have to apply for, and NASA kind of opens it up for people who have social media platforms to go to launches, image releases, stuff like that, because I think they're starting to recognize that social media is a really big way that people learn about stuff that's going on in the world. And so you get invited and you have similar access to news media. And so I was looking at the requirements and I was like, I actually kind of meet these. I have platforms now and people who know me and my content. And so I applied, and I was actually initially waitlisted because they cap it at 100 people, and they had thousands applying this year.
Oh, yeah.
The Artemis 1 launch is such a big deal. And then I got off the wait list somehow. And so, yeah, I'm flying out to Florida in a couple weeks. And it's a multiple day event, and we'll see the launch. And I'm very excited because I've never seen a rocket launch. So it's going to be amazing. Yeah.
That's awesome. How do you feel about us going back to the moon? How hype are you?
I'm very hype. I'm very excited. I think that it was something that really sparked a lot of people's curiosity and imagination when it first happened, and got a lot of people re-interested in space and space exploration. And these kind of moments can do a lot for the field as a whole, regardless of whether you're interested in being an astronaut or studying the solar system, or like me, studying stuff way beyond the solar system. It's just an exciting time to be in the field in general.
Yeah, definitely. This stuff also just brings a lot of technology to the lay people as well. So
Yes.
it's super beneficial.
Oh, for sure.
Yeah, wow. Is this like the extended stay mission, or is this like just getting supplies to the moon? Like, what is the first launch?
Yeah, so this one is kind of more of a testing launch to test both
Okay.
the SLS rocket system and the Orion spacecraft, the actual module that will have astronauts in it. So they're going up to the moon. I think they're doing 6 laps around it, something like that, just to test the spacecraft, the navigational systems, all of that, and then coming back down. But there's also a lot of science goals involved. So I forget the number, but there's going to be several of what are called CubeSats, cube satellites. They're kind of very small satellites that are very dense in the amount of science that you can put on them. And
Mhm.
so they're going to put those in orbit around the moon so that there's actual like scientific goals associated with this mission too, not just testing the spacecraft.
Well, of course, yeah. You just don't want to send like a few
Just
$100 million rocket just to fly around.
yeah, exactly.
I think we're past that point.
Yes.
That was the '60s. I
Yes.
think we're good.
Hopefully we're past that point.
Yeah, and the really cool thing about this is it's not really driven by, how do I want to say it, like external factors, right? Like in the '60s and '70s, it was kind of more of like a Cold War-esque
Yeah.
response,
There's a
whereas
lot of
here it's more humanitarian. It's more just scientifically driven, and it's yeah,
yeah.
it's a little bit better. But it also took us how many decades to get back to this, which shows how influential military is
Yes.
to this part of science, which is sad. But good to
Yeah.
see that we're getting over that now.
I mean,
Hopefully.
it is kind of amazing that we are getting back there considering the difference in the amount of funding that NASA had in the 60s for the Apollo program versus now. There was just way more resources available.
Yeah. Oh yeah. They, not we. I'm not a part of
Yeah,
it.
we're not
they
responsible.
they have done a lot with a little. It's very
Yes.
impressive.
Yeah.
Considering, like, if you look at the budget breakdown, you would be surprised, like really surprised.
There's pretty much nothing going to NASA at this point.
Yeah.
Yeah.
Yeah. Kudos to them. So we're talking about galactic evolution, and I wanted to start off by talking, in terms of, the cosmology, the escapades of the universe from the start of, I guess, the border of ignorance and knowledge, right? We kind
Right.
of like disregard what happens before the Big Bang, but then we're very knowledgeable in terms of what happens after that moment, right? Um, what, from my understanding, and of course this is 1,000-foot overview, is what's very integral to your research in galactic evolution started with the inflation period. Am I correct by saying that?
Yes and no. So it galactic evolution and the field of extragalactic astronomy in general is very, very broad. There's a lot of different things that you can do. So I'm actually focused more in my specific research on galaxies that have already been formed, they're doing their things, and we're talking about galaxies that are like 10 billion light years away from us now, whereas the very first ones were 45 billion light years away. So I'm not
Mm.
so much focused on this initial period and the impact it has, but it does have an impact on galactic evolution in general.
Right, right. And that, I mean, it makes sense. It's kind of like the seeding, right? Of we're not living in an isotropic system. If we did, matter would be everywhere and we wouldn't really have coalescence.
Right.
So yeah, this
There
is kind of the starting point, I guess.
Yes, the density fluctuations that happen in the very first tiniest fraction of a second of the universe lead to the creation of everything that we see now.
Right. And do you subscribe to the notion that this was a quantum field fluctuation of like the inflaton field?
Yeah, so this is getting outside of the realm of, what I know a lot about. That is probably the best understanding that we have is these quantum fluctuations when the universe was kind of operating on a quantum scale and everything was in a really small area. We're talking the entire universe in a region smaller than a grain of sand. Like
Yeah.
that's how tiny we're talking here. And so any kind of fluctuations that happened in kind of that quantum realm, and then they get blown up to larger scales during inflation.
Right, right. And a good way to visualize this for the person that's listening or watching it is like just look up an image of the cosmic microwave background, and then you can see the differences in the densities. And it shows like it's like a hot and cold map.
Yeah.
Obviously, we realize that hot and cold difference is extremely minuscule. It's like super, super
Yeah,
small,
it's
but it was a difference. And it shows the densities, the local fluctuations in densities, which then arises to these how do I want to say it, right? Like after the cosmic microwave background, we get into the dark ages, right?
yes.
Yeah. How influential is that period to the starting of these galaxy formations?
So that's something that we don't really know. Like the idea of how do galaxies form is something that is a big field of study right now because
Yeah.
we really can't see much of what's going on there. That's one of the reasons JWST is so exciting because it can actually see some of the first galaxies that formed and give us
Mhm.
an insight into what sort of structure was in place that allowed these galaxies to form. So the idea of the dark ages is that essentially for the first maybe few 100 million years, we're narrowing down that time limit with JWST. The universe was pretty much just hydrogen and helium, and it was relatively cool and it was expanding. There were no stars, no galaxies. It
Mhm.
was just kind of gas. And then at some point, that gas started to group into little seeds that became stars and galaxies and kind of lit up the universe.
Right. It's just a sequential way of the universe getting cooler and cooler, and the physical response to that cooling. These cooling gaps. I guess probably a good way to put that.
Yeah, it's because in order for gas to kind of cluster and collapse gravitationally, which is what is needed to form stars, it can't be too hot because if it's moving too fast, that kinetic energy will kind of overpower any gravitational attraction. So you have to let the universe cool down. And it took a couple 100 million years. Yeah.
That's crazy. And
Yeah.
you think about it, right? The Dark Ages is technically really, really long, like about 1.7, 1.6, no, yeah, 1.6, no, 106. Oh my gosh, sorry. 380,000 years after the Big Bang was the cosmic microwave
Yes.
background. And
Yes.
then the earliest galaxies was between 100 to 200 or more close to 200 million years.
So this is something that we don't actually know, and it's something that JWST is really big for is finding these earliest galaxies because models predicted maybe within 300-400 million years, but JWST is seeing candidates. None of them have been fully confirmed yet, but the candidates that might be from just like 200 million years after the Big Bang, and so we're kind of figuring out how long that dark age period is by trying to figure out how far away these really, really distant galaxies are. And it's not something that we know for sure.
So Glass Z13 was a galaxy that I highlighted in one of my TikTok videos, and the sources said that it was 13.5,
Right.
but like that's still like 300 million years after the
The
Big
Big Bang.
Bangs. Okay,
Yes.
so is that not confirmed then, or they're just looking for something even
They're
earlier?
they're looking for something even earlier because some of the
Hmm.
JWST deep field candidates, they think from photometry might be more like 180, 200 million years after the Big Bang, but there's pretty big error bars on that. The really only way we can get a narrowed down age is through spectroscopic data, which we don't have for a lot of those galaxies. We have kind of essentially lower resolution spectroscopy with photometry where we can make guesses of how far away this thing is.
That makes sense.
Yeah.
Okay, so there's also a lot of speculation on the influences of primordial black holes and with dark matter that come into the first sort of formations, like the influence in the dark ages to
Right.
create these galaxies, right? There's a lot of there's a lot of speculation. There's a lot of back and forth, and there's a lot of theories on how much has, how much is out there, because primordial black holes, we haven't found them yet, right?
No. So
Yeah.
this is the theme of this should just be what we don't know, because that's kind of what's going on in galactic evolution. But almost every large galaxy that we see today has a supermassive black hole in the center of it. And I'm talking millions of times the mass of the sun, really, really big. And we don't fully understand where those come from. And so that is an issue. There are also objects called primordial black holes, which are thought to maybe form in the first couple seconds after the Big Bang, that are smaller than that, but there's lots of them. But we don't really have any evidence that those exist, and people kind of debate back and forth. The reason that this is important is because a big part of galaxy formation is kind of using dark matter as a foundation. So those density fluctuations we were talking about that you can see in the CMB, they manifest in where dark matter is in the universe. You have regions of denser, lower density, and dense regions of dark matter attract the gas, which then can collapse to form the stuff that we can see. And so if dark matter is primordial black holes, then it's important to kind of figure out how many of them they were. People debate because some people argue all of those black holes would have merged. And so we would see a bunch of evidence of merging primordial black holes with
at like LIGO.
Yep.
Yeah.
Other people argue that the evidence we have seen from LIGO suggests that they're primordial black holes, but gravitational wave astronomy in general is a very new field. So
and something that's not really guaranteed is like, okay, if you're getting these cooling stages after the Big Bang, then there's material that could possibly coalesce into these primordial black holes, which then have stages of size. Right. And then, but the question is like, okay, if there's stages of size, how, what are we supposed to reconfigure the stellar mass it takes to create a black hole in different stages, which is something that's also being questioned, right? Right.
So one of the interesting things about primordial black holes is that they could be very small, like much smaller than our sun, even smaller than like the Earth in terms of mass, because they wouldn't form from stellar collapse. They would form just from whatever high density regions there were in the early universe. So that changes kind of our understanding of black holes, because all of the ones we see today are either these supermassive ones in the center of galaxies or the ones that form when really massive stars collapse under their own gravitational pressure, which are like 50, 80 times the mass of the sun. But we don't really see anything smaller than that.
We need a lot more data.
Oh, for sure. But the problem is, it's really hard to get any sort of information about black holes or any object that doesn't interact with or emit light, because that's how we do most of our astronomy, is with light.
Right.
Yeah.
It's interesting to also think about, okay, if you have all of these primordial black holes, they would have to merge at some point, which could possibly have led to the supermassive black holes that helped aid to the first galaxy formations. It's hard.
But then if they all merge into supermassive black holes, then they can't be a dark matter candidate, because there's a ton of dark matter that is not the supermassive black holes in galaxy centers.
What an interesting age of science we are in.
It really is. It really is.
So cool. And I guess if we haven't blown anybody's mind already talking about all this stuff, I mean, you have to think about it. Like we're theoretically proving these things before we can visually see them, but you need visual and theoretical mathematical proof along with visual proof to make something actually a thing. Like I saw in one of your TikTok videos that you were talking about, like, this is what theory means in science. And I was like dying. I'm like, everybody says I have a theory. I'm like, no, you have a hypothesis or even a thought. Like hypotheses at least have
some sort of backing.
Yeah, something that makes sense, right? But like theories have to have visual and, mathematical evidence and
Yeah.
have to be trialed many times with peer review.
Yes.
So,
yeah, a theory in science is very, very robust. And I think that is something that a lot of people miss when we talk about things like the theory of general relativity or the Big Bang Theory. They're not just random ideas that somebody came up with. They are things that are backed with tons and tons of evidence.
yeah. And laws are something that are set in stone. They're objectively true.
Laws they're more
ahead.
mathematical usually. Laws will explain what happens when you put something in orbit around something else, and then the theories explain why that is happening or like how that is happening.
And theories, in my opinion, this is opinionated, that are something that's not really ever safe. They're because we're still like really, how do I want to say, not dumb, but we're still in the dark. So like every day, like people are trying to set out to disprove things because that's what you do in science.
That's
if you
science
can't disprove
works.
it, you're good.
Yeah.
Yeah.
I will say laws are also kind of subject to that because some things like Newton's laws of universal gravitation, they don't actually work in every situation. Like they don't perfectly describe like Mercury's orbit, for example. And so there are adjustments that can be made to the math where it's like this holds in these conditions, but not necessarily everywhere.
Right. Yeah. If you think about it, you're good to use Newton's laws for building a building on Earth.
Right.
But you're not, but like vice versa. You can't do that using relativistic, phenomenon.
Right.
Yeah. So sorry, let's get back on track here. Let's talk about something that we know a little bit more about, right? We're talking about galactic evolution in terms of what happened after, the first galaxies have formed. So you want to kind of run me through the stages?
Yeah. So, you say we know more about it, but we still don't know everything about it.
A little bit more.
Yeah. So there's a couple of models about how galaxies form and evolve. You can break them into kind of top-down models where you start with large-scale structure and that breaks up, and then bottom-up models which start with smaller structure and then they combine and merge and form bigger things. The top-down models were kind of the initial ideas, like there were giant regions of gas that collapsed and formed galaxies. That doesn't seem to align super well with evidence. We think that the very first galaxies that formed were these smaller regions, kind of more like globular clusters, and then they merged and formed bigger things. And typically when things are merging and there's a rotational aspect in that, they start to flatten out. Think of spinning like pizza dough. Right. And so a lot of these first galaxies we would think would be kind of more disc-like our own Milky Way, a little bit of a flattened pancake. And then they start to merge more. And then when you have those pancakes that are merging at different angles, you lose that flatness, you lose that structure, and then you can form ellipticals. So those are kind of the two main types. You've got the spiral flat galaxies and then the ellipticals, which are just kind of like blobs. So that's one idea. There's this kind of evolutionary path from spiral to elliptical, but there are also elliptical galaxies that we see very early on in the universe. And so trying to understand how those could form without necessarily coming from spiral galaxy mergers is something else that is being worked on.
Yeah. Interesting. So yes, and then also like you were talking about how galaxies can merge and become larger. That's a very, very long process.
Oh, yeah. Like for a couple billion years. It depends on the galaxies, but yeah.
Right. Like a good example of something that will happen in a few billion years is like Andromeda and our galaxy, the Milky Way, colliding. Interesting. I've seen the models on that. I'm like, man, that's a hefty collision, and there's just stuff scattered everywhere. It's like, ooh. I'm glad
so
I'm not
a couple. Our solar system pretty much won't be. That collision is going to happen at around the same time that the sun dies. So there'll be a lot
timing
going on. Yeah, but when galaxies merge, like two spiral galaxies, if we think Milky Way and Andromeda. One of the important things that we talk about when we talk about galaxies and their evolution is what's going on with the stars inside of them. How many new stars are being formed? What are they doing? How bright are they? And so when two spiral galaxies form, there's a lot of dust and gas in between the stars. And during collisions, that gas gets compressed and we get huge bursts of star formation. So a lot of times galaxies that are merging are really bright. There's a lot of new stars being formed, and you kind of get this really beautiful patterns, and then those stars will slowly die out. And elliptical galaxies, they don't really have a lot of gas in between stars. Elliptical galaxies don't have star forming material. That's kind of, we call them red and dead. They're redder stars, and they don't form new stars. And so after a collision, all of the gas gets used up in forming these new stars. And then once those die, you don't have much left. And so you get kind of these stagnant blobs.
That's sad.
I know.
So we love spiral galaxies. They continue to go. Yeah. Okay.
They're the pretty ones. They're the ones that form stars because they have a bunch of gas and dust.
That's fair. So let's think about it this way, right? If two spiral galaxies are coming, you have to think about maybe I might be wrong by saying this, but spin, right? Spin, as well as the action of when the black holes, the supermassive black holes in the center, come in collision. Like, how is it colliding? Is there going to be not obviously an immediate merger, but are they going to become binary? You know, there's possibilities that way, which could help seed, better seed, like formations of stars.
Yes and no. So, you know, if there's like binary black holes in the center of a galaxy spinning around each other, you have these kind of pressure waves that can get pushed out from them, and that can move star-forming material out into the galaxy, but it can also push it all the way out of the galaxy, which you can't form stars out of. And typically we think most, like when two galaxies merge and their black holes start orbiting around each other, that's going to decay pretty quickly and they are going to merge. We don't see a lot of super stable binary systems. We do see them, but it's thought that especially in merger situations, they would just eventually combine and form one.
Almost like a static collision, you think? Do you think it's more static collision versus this binary action? Like, so, it's more probabilistic?
This is outside my area of expertise. I will just say that. I'm speaking off of what I have heard from talks and trying to remember. But there is this binary spinning that happens, but those orbits just kind of decay over time. Yeah,
that makes sense. Over a long period of time. Like in our,
in human scales. Astronomical research tends to skew what long means.
That's fair. I also love the fact that we say like the death of stars, the death of galaxies. Like, I didn't know that they were dying. It's interesting.
Yeah, and I mean, in some sense, they're really not. Star death is typically just whenever they are no longer like in a stable equilibrium. And what that looks like depends on how big the star is. Really, really massive stars will go supernova. They'll explode, and that's a pretty extreme like death. You're not coming back from that. Smaller stars like our sun, when they die, they'll just kind of gently push away their outer atmospheres, and the core will be left over. So you will still have that in the form of a white dwarf. And you can even have supernova remnants that are left over like neutron stars and black holes, but they're just kind of no longer doing the normal star thing. So we say they died. With galaxies, galactic death isn't just like, you know, all the stars kind of move away from each other and there's no longer something there. Typically, we call galaxies dead when they're no longer forming new stars, but they still have tons of stuff in them. So really small stars live for, we don't even know how long because the universe isn't old enough. So essentially, they've been doing their same thing for 14 billion years. They'll keep doing it for a long time. That galaxy will still be there. It just won't be producing new stars. And so we call it dead, which isn't maybe the best description.
Right. I mean, you think about all the stars that are in even just the Milky Way galaxy. What is it, like anywhere from 100 to 400 billion stars?
Yeah. I think that's
obviously it's a big level of uncertainty, but like, you know, can
a
only
lot.
Yes,
There's a lot.
There's a lot. So even if there's not new stars being formed,
There's a
it's
lot.
I think it's okay. And even stars last a very, very long time.
Yes.
In our
Our time
perspective of time.
scale.
Yeah.
Yes.
Yeah. So maybe it would be good to talk a little bit more about what you do in terms of galactic evolution research.
Yeah.
So hit us with that.
Okay. So, I was talking earlier about how galaxies, we think, have this kind of bottom-up formation where
Yeah.
little bits come together, they form a galaxy, galaxies merge, they get bigger and bigger over time. That's what we would expect. But when we look out at the universe, we see this effect that's called cosmic downsizing, where galaxies do get bigger and bigger over time, and then they start getting smaller and smaller. And so the question is, what is causing that to happen? In this kind of hierarchical formation, we would expect these continued mergers to keep bringing things together, more star formation, more stuff. And so my research specifically is looking at how active galactic nuclei, or AGN, which are these supermassive black holes in the center of galaxies that are actively eating stuff up, can end up shooting material out of the galaxy. And so the galaxy is losing that star-forming material, and so it's getting smaller. It's losing that gas. So both AGN and like supernova winds are thought to be able to do this, to push gas out of the galaxy so that it can no longer form new stars. But the actual mechanisms of how that really works isn't fully understood. So my research is very computational heavy. I use simulations. I model galaxy evolution on super large scales, and like I'm talking thousands of galaxies in one simulation, and kind of vary parameters about what those AGN are doing to see how that affects kind of what the gas around the galaxy looks like. So that's like the main part of my research, and then we'll compare that to observational data. You were talking about this earlier, the need to work in theory and observation, because when we look at a galaxy, we can like see it doing something, but we don't necessarily know what's causing that without doing modeling and then comparing those models to the observations. So we can be like, oh, okay, we're seeing this, which we only see in simulation when we set this parameter, which means that's probably what's going on in this galaxy.
Gotcha.
So that's sort of a big picture goal of my research, is to compare it to the observation.
Yeah, super exciting. Two main points I think I want to put out. Well, maybe just one. Is that, yeah, like you said, it's very tough because there's a lot of stuff going on. It's an extremely dynamic situation. You have so multiple supermassive black holes, or multiple just like regular like smaller black holes that are creating this this throwing effect.
So this is typically just one supermassive black hole in the center of the galaxy. Yeah.
Okay.
These aren't necessarily galaxies that have undergone a recent merger or anything like that. They're just big galaxies with stuff falling in towards the center. And so when you have stuff falling in around a black hole, it kind of spirals around it, and all of those moving charged particles create really powerful magnetic fields, and it's those magnetic fields that end up pushing stuff out of the central region of the galaxy.
That makes sense. Okay. Yeah, because I mean, even if you had something that supernovaed right and towards the inner portion of the galaxy, it would end up falling at some point into the black hole, which it's pretty much an I hate saying eating because people get like so afraid of black holes.
But they're not that. Yeah. They're not like vacuum cleaners. They don't have like a range of suction. They're gravitationally like powerful. But if you were to replace our sun with a black hole of the same mass, we wouldn't fall into it. We would just keep orbiting around it. Like we would be fine, but we wouldn't have heat. But yeah.
You would only have heat until you got like towards the event horizon, where stuff's literally plasma. So you wouldn't die by the spaghettification. You would die by just the plasma ripping you apart, etc., into fundamental particles. But You're not going to get eaten.
It's not going to happen. Don't worry. The sun is not going to turn into a black hole. We are going to be fine.
Yeah, isn't it supposed to turn into a white dwarf, actually?
Yeah, it's way too small. So you have to be about, well, this is another thing that's kind of debated, but 30 to 50 times the mass of the sun to get into regions where you might turn into a black hole.
Yeah, that's fair.
Yeah.
That number is a little variable. Yeah.
Yes. Yeah, it really is. All of these are.
Yeah. So, do you have anything else to say about your research before we move into commercial break?
I don't think so. I think it's just important to highlight. I think a lot of people think astronomy is just using telescopes and might not realize that there's a lot of other types of research that you can do in the field. So, like, I will never have telescope time during my PhD because I don't need it. I use supercomputers and run these simulations and analyze that data, which is pretty much just as important as the telescope time when it comes to understanding what's going on.
Yeah, I mean, so that's a good point. Like, science is collaborative. You don't have to do you don't have to do everything to be able to, it's a collaborative work. But
Yeah.
I'll just go with that, and we can end it there.
Perfect.
Awesome. So when we come back, we're going to be talking a little bit more. We did a precursor there, about like dark matter in the dark ages. So we're going to talk a little bit more about dark matter when we come back. So stick around. This is segment 2, and we're going to be talking about something, again, that we don't know too much about, but there's a hell of a lot of hypotheses out there. We're going to be talking about dark matter. So I guess I kind of structured this to say, like, this is, again, like, Galactic Evolution 101. This is going to be Dark Matter 101. And we might be talking about some of the postulated ideas of dark matter that are still considered, they're backburnered, or they're just completely thrown out.
Right.
Yeah. So do you know anything about the history of the discovery of dark matter?
So I'm trying to remember which came first. There's a couple key pieces of evidence for dark matter. One of the biggest ones is something called the bullet cluster, which is actually 2 clusters of galaxies, each containing like thousands of galaxies. And they kind of ran into each other, and they kind of passed through each other. And they have this gravitational lensing effect. So we can see how their mass warps light from background galaxies. And looking at how much the light gets bent and the angles of that can tell us how much mass is there.
Mm-hmm.
The problem that we quickly realized was when you look at all of the stars and gas and dust, the stuff that we can see in these galaxy clusters, and added up how much mass that is, and then thought about how much mass is needed to create the gravitational lensing effect that we saw, those numbers don't line up at all. Mm-hmm. There was tons of missing mass. Yeah. So it's like, okay, there's something there that we're not seeing. Another piece of evidence is looking at how spiral galaxies rotate. These galaxies are spinning, and typically there's a relationship between how far away you are from the center and how fast you are orbiting. We see that in our solar system. It's a great example. The further out a planet is, the slower it is orbiting, because of essentially how these laws of gravitation work. Your velocity depends on how far away you are from that central mass.
Yeah.
But in the Milky Way, instead of seeing stars kind of trail out, we saw them keep up pretty high speeds at outer edges, which suggested that there was more mass and more mass further out that we weren't seeing. And this sort of evidence we see all over the place now. Any sort of gravitational lensing effect, any sort of spiral galaxy rotation curve, there's about 5 times more matter that we can't see than the matter that we can. And so that's what dark matter is. It is this matter that we can't see. It doesn't interact with light. It doesn't emit, reflect, absorb, like nothing. But there's tons of it out there.
Yeah. That's pretty crazy.
Yeah.
Even the bullet cluster that you talked about. So this was even, I think, visualized before that, like 40 years before that. And then again, it was revisited because people were like, you're freaking nuts.
Yeah.
Like, man, we can see everything. It's all like matter is visible. You don't know what you're talking about. And then 40 years later, there was, I I forget, there was a man and a woman like a team of astronomers that found this gravitational lensing, and I think it was what Einstein's ring was a lot larger than what they anticipated
Yeah,
from that collision event, and they're
right.
like,
Why?
wait a minute, why that's not right, that doesn't align with the equations, and it doesn't
Yeah.
align. And yeah, they found that in that cluster there was what 85% of the matter just missing.
Yep.
Whoa.
Yeah.
You know?
That is not insignificant.
No,
Yeah.
yeah. And spiral galaxies, the stuff on the end it's a moment arm, right, from the center, and it
Right.
should be moving a heck of a lot slower, right? Because if you just sit down and put your elbow on the table and move your hand relative to your elbow,
Right.
things have to move, like things move at the center, like more closer to the center, a lot faster than
Faster.
what's on the
Yep.
outside. And it moves practically at the same rate. It's a disk moving, like, it's how do I explain that better? But it's just moving at the same speed, close
Yeah,
to the same
close to-
speed.
which
So,
is not how it should be.
right. And
Yeah.
there's thought that there's this 85% mass that's missing, that's pretty much making it to where these are relatively moving at the same speed, based on its like inner radius versus the outer radius, right? It's kind of minuscule in the difference between what's actually the outer radius and what's
Right.
now more towards the inner radius.
So it's thought that pretty much every galaxy sits in what we call a dark matter halo. So you can kind of
Yes.
envision this bubble that every galaxy is in, and those bubbles are much larger than the actual galaxy that we can see. And so because there's more mass further out, that effectively helps speed up the outer regions.
Right. So we've talked about like how it was detected, but like it's dark for the reason that it doesn't interact with electromagnetism
At all.
at all, but it has gravitational influence,
Yep.
which is pretty wild. It's something that's not really, it's very interesting, right? Because if you're, I want to get this correct or remotely close, but if you don't have a or a electromagnetic influence, that means that your charge is neutral.
Right. So that's part of it. There's
Mhm.
also, you can be neutrally charged, but still like reflect light, like dust grains.
Yeah.
You can be
Good point.
neutrally charged and absorb radiation, just like a single atom that is neutral between the protons and electrons will absorb photons. But
Mhm.
dark matter doesn't do that.
That's wild.
Yeah. It is wild, but part of me is always like, I mean, why not? Like,
That's fair.
who says that everything has to be so interactive with electromagnetism? Like, why couldn't there be a particle that doesn't?
Right, right. So do you subscribe to the notion that this is also interacting with the Higgs field, or do you think this is a totally new quantum field that they have to discover?
So now we start talking more about what the dark matter candidates are and like how related are they to baryonic matter, which is normal matter, not photons, protons, neutrons, electrons, the stuff that makes up our universe. How interconnected are these things? And I honestly, like, we don't know really. So it's yeah, we don't know. Some of the theories that we'll probably talk about have some weak interaction between baryonic matter and dark matter, outside of just like gravitational interactions. So
Yeah.
they
Yeah.
are connected, but others aren't.
Yeah, and there's at least, I think, from my estimates, at least 50 some large scale detection tests going on right now for dark
And
matter all over the
all
world.
of those rely on the fact that dark matter does interact with baryonic matter in some way that will be detectable, but we don't know that for sure.
Yeah, and that pretty much runs on the precipice, like what you were saying, of weakly interacting particles, right? WIMPs, weakly interacting massive particles.
Yes.
Right. So they're assuming that they have large mass, massive, because of their gravitational influence. right?
Yeah, so
Mhm.
there's kind of two genres of dark matter, you could call it. There's cold dark matter and hot or warm dark matter.
Okay.
And the difference is just the speed at which the particles move, which is often correlated to their mass. The heavier a particle is, the slower it moves. Massless objects like photons are the fastest things in the universe. So small mass can move faster. We know that like there has to be some variant of cold dark matter because we see it clustered gravitationally. If you have dark matter
Mhm.
that is warm and moving really quickly, it wouldn't be able to cluster in the way that we observe. And so this kind of cold dark matter vision for our universe is by far the most popular, aligns the most with observation. And the best candidate within that, most commonly, it's a candidate is the WIMPs, which, yeah, like you said, it's just these particles that are reasonably massive and they weakly interact with each other and can kind of form these bound clumps.
So again, I will jump back to what you said earlier. Okay, why couldn't there be like why try to rule something out? Why not have both? Why not have cold and hot dark matter? Why not have a completely dark set of atomic particles?
That is absolutely a possibility. Like, there are people who think that it could be a combination. The problem with that is that we can much more easily constrain cold dark matter models.
Yeah.
Constrain just means things like how massive can these particles be, you know, how strongly can they interact with normal matter, how much
Hmm.
can they interact with each other, other dark matter
Hmm.
particles. Because the places that we observe dark matter are in these kind of gravitational clumps, it's a
Hmm.
lot easier to constrain cold dark matter. But that doesn't mean there aren't other particles that move quickly that don't interact with light.
Yeah, they could be like more like a neutrino, you
Right.
know,
And that was
where
actually thought they were a candidate was neutrinos, but that's kind of broadly ruled out at this point.
oh interesting.
Yeah. I mean, at least in the sense that neutrinos are very, very small and very, very
Mhm.
fast, and they wouldn't
Yeah,
be the same
it's
kind of clumping effect.
right, right, totally opposite.
Right.
Absolutely. And you only get like they're very weakly interacting. I mean, you get interactions every once in a while, and it just depends on its right. It just depends on its spin relative to the Higgs field and
I think
something.
so. It's
Yeah,
been a
it's
while since I took particle physics.
it's an intricate, and honestly it's something that's still kind of debated on how neutrinos end up getting mass every once in a while. It's not like and they have very minuscule mass, so they
Yeah.
don't know if it's something like an alternative to the Higgs, or if it's an anti-neutrino pair that finally gives them interaction with the
Mm,
Higgs. It's it's still kind of actually being debated. There's also with dark matter detection, they're still trying to figure out this mess.
right.
I know one of the leading sites for that is the LHC, so
Right.
that's still ongoing.
Which
But
is very much out of my field is that particle
I'm j-
accelerator work, but it's fascinating.
I'm just a fanboy right now. Again, I
That's
have to,
fair.
but like it's fun. Like a lot of these postulates then emerge the woo woo kind of things with
Mm.
with dark
Opening
matter.
portals and is it consciousness or yeah.
It's always consciousness. But yeah, like is it like the fourth dimensional is it like a higher dimension seeping into, or is
Right.
it like a, how do I want to say, is it bridges between,
Universes.
yeah, parallel
I've heard that
universe.
like dark matter is a parallel universe just barely connecting with ours, so we
Mhm.
see like weak gravity. But the much more likely view, in my opinion, is that it is just a particle that doesn't interact with light, and so we're trying to understand what that would look like.
Yeah,
Yeah.
super interesting. Yes, there are a lot of possibilities, but definitely like mainstream science has, that in their pockets as being the largest possibility. Now it's just up to observational data. Like, can we get this?
Yeah.
Tough, very tough.
Very tough, for sure.
But there's definitely, like, I was running through some papers and I'm like, wow, there is a lot of things, like specifically, like I have here, that people were thinking that dark matter, like we talked about earlier, was these clusters of primordial black holes.
Right.
And the only thing with that is that they were claiming this, and it's still kind of a backburnered idea, obviously,
Right.
because that hasn't been solved yet. That there's a lack thereof of these WIMPs, in, like, they haven't detected these WIMPs, so maybe
Right.
it is
It
that
is
possibility.
something else. Yeah. That kind of whole possibility falls under this macho idea, which was like, you have WIMPs and then you have machos. Macho is massive, compact halo object, and so something that is massive, but either doesn't emit light or is just really hard to detect. So for a while they thought maybe there were just a bunch of white dwarfs and neutron stars, which are these stellar remnants that are very, very dim and very small. So it's hard to see them. So maybe we just couldn't see them. And that was what was responsible. And primordial black holes, or black holes in general, also fit into that category. The problem is we know what creates white dwarfs and neutron stars and like stellar mass black holes, and there's just not enough stars in the universe to have made enough of these machos to account for dark matter. So all of that has been backburnered. Primordial black holes is kind of hanging on.
And literally their only argument, I won't say only, but like their leading argument is just the lack thereof of WIMPs. Or
yes, we haven't found a WIMP, so maybe it's this. There are worse arguments, but there are better arguments.
Yeah, I love the acronyms. I was laughing a little bit because, like, we keep saying WIMPs and machos. It's so funny.
Acronyms are fun in science.
100%. Yeah. So let's transition a little bit. Maybe you've precursored this a little bit. Do you want to talk a little bit about your research in dark matter?
Yeah, so in undergrad, I worked with a physics professor at my school who focuses on this one very specific model for dark matter that falls under a category called self-interacting dark matter. So objects like WIMPs kind of tend to fall a little bit more on less interaction, what we sometimes called a cold collisionless dark matter model, where the particles can weakly interact through gravity and with baryonic matter, but they're not like bouncing off each other a bunch. Whereas self-interacting dark matter, it can scatter with itself. You can think of, these particles bounce around and they transfer energy and momentum to each other. And even more extremely, they could form bound states. And so that was the focus of my research. And this is possible under what we call an asymmetric dark matter model. And it has successes compared to WIMPs. There are certain things that WIMP and generally cold collisionless dark matter models can't explain, including things like the distribution of dark matter in the centers of galaxies. It's more flattened out than we would expect. We'd expect there to be kind of a peaked profile where like there's a lot of it, but it's a little bit more flat. And one way of explaining that is if dark matter could kind of bounce off of itself and kind of distribute that energy and density, it could flatten out that profile. The asymmetric dark matter model specifically comes from the idea that in the early universe, there was an asymmetric amount of particles and antiparticles, just like there were for baryons. And so it kind of helps link these two things. It's actually very good at explaining why there is a baryon asymmetry, because there's also one in the dark sector. And through a lot of kind of technical particle physicsy things, depending on how you model it, you can create large bound states. And so the research we did was assuming essentially just some scalar mediating particle that allows two dark matter particles to bind and no repulsive forces. So under this model, you could get groups of billions of dark matter particles kind of clumped together like the nucleus of an atom, but you wouldn't have that electromagnetic repulsion that limits how big atoms can get. So you could get billions of them.
Wow.
So that was the framework of the research. And then my specific work was figuring out whether there would be any kind of bottlenecks in the early universe to how big these things could get, because we do see bottlenecks in baryonic matter. There's a reason there's only hydrogen and helium in the early universe, because getting past that helium particle is difficult for a number of reasons, mainly that helium is a very stable configuration for an atom, and anything larger than that wants to decay into helium. So the question was essentially, would there be a similar thing in the dark sector? And so looking at where in the parameter space for like mass and self-interacting parameters you would have to be to avoid bottlenecks. So that was my research.
So that would be running, wow, this might be bad. This is running off the assumption that there is a flip to like the baryonic matter. There's like a kind of a symmetric version of dark matter particles.
Yeah, like there's a whole
electromagnetic interaction.
Yeah, so like there's a whole dark sector. So not just one particle, but you have the particle and then you have mediating particles. Like we have the W and Z bosons that mediate the weak force in our like normal matter. So there would be similar mediators in the dark sector. And so you could have more self-interaction than in other models. And there are certain kind of like observational smoking guns for any sort of dark matter that forms a bound state, but we haven't seen them or have the capability.
Interesting. And if you think about it, like in the way that you've approached, rather than having light emitted whenever you have collisions, it's just completely embodying that energy, right?
Yeah. So this is, again, maybe there would be some signature, like would there be some sort of heat lost in those interactions that we could detect? With all of these models, I should say, there are a ton of different sub-models. So like we worked on one specific version of an asymmetric dark matter candidate, but there are other ones that have repulsive forces or ones that have weaker mediators. So there's a huge variety in these models, and essentially it's all just mathematical work trying to figure out how these things would interact, what they would look like, and then just waiting for our observational technology to catch up, and or for a direct detection experiment to work.
Yep, makes sense. Well, all of it has to start usually mathematical. So, I mean, Einstein's general theory of relativity. Right. Yeah. Relativity was it like 5 years after that he wrote out his postulates of relativity? I'm pretty sure it took a while, but
still like continuously getting evidence that supports it. Like gravitational waves was something that he predicted, and it took almost 100 years to actually detect those. So you definitely, in science, there's not always a immediate gratification.
Oh no, that was just an example. Like you start mathematically proving something, there's evidence, and then it just
you refine and build and
yeah, definitely. Wow. Okay. So hopefully if people are still hanging on after I don't even know if we should recap. We should probably at least say that dark matter is something that's still there's so many avenues to that. Like there's probably more avenues to dark matter than there is to like what we were originally talking about with galactic evolution.
Because there's just a lot of possibilities. One that we haven't talked about that I do want to mention is the idea that we are wrong about gravity. So there are people who are working on like modified gravity, which means that there isn't actually any dark matter. It's just that the math that we're using to predict the gravitational influence is wrong. Personally, I don't think that is very true, because we just get more and more and more evidence for kind of a general relativity understanding of gravity. all of the technological advancements, the gravitational wave detectors, the images of black holes, JWST's predictions, all of it is lining up super well with what general relativity. So modified gravity is a way of explaining dark matter, but it is, I think, considered a little bit more of a, I don't want to say fringe, but just not necessarily as robust of a model as actual particles.
Yeah, I mean, if you even just think about it this way, that would be refuting almost a century's worth of mathematical and observational data.
Yeah.
Which it seems outlandish. Like, and I don't mean to be rude about it, but like I just wouldn't. That wouldn't be the first thing I would subscribe to.
Exactly. And for me, it's always like, well, I think it's much more likely that there's just a particle that doesn't interact with light. Like that makes a lot more sense than we are completely wrong about gravity.
My evolved ape brain wants to go with something that's more makes a little bit more sense to me practically.
What is that principle? The simplest answer is usually the right one. There's a word for that. Have you heard that?
I have, but yeah, I'm not a
philosopher.
I'm not a philosopher. I don't. Yeah, I was gonna bring that up, but I didn't know. That's not really woo woo. I mean,
no. I think that it has its place in science right now, especially when things start getting super, super theoretical math-y, where things can get made really complicated. And there's arguments for both sides of like, there's no reason the universe would say everything should be simple and beautiful. But also, like, if you're having to really stretch to make things fit, maybe that's not, it's the philosophy of science is tricky and not something I am very
I mean, I guess the last thing I'd probably want to say is that you gotta have the people poking in all different directions. If you don't poke in all different directions, then there's more uncertainty. So why not just postulate it and say, okay, well, the evidence doesn't support this. Let's put it on the back burner.
Right.
Not this, higher dimensional link to the parallel universes thing. That's outlandish, but like
and more importantly, that's just something that we couldn't test. And like a key part of science is you want to do work that could at least one day feasibly be testable, because otherwise you're not really doing science at that point. You need to find evidence.
Right. 100%. So with that, we're going to end dark matter. And when we come back, this is going to be a little bit more miscellaneous. We're going to talk about Skylar's education research, and then also a little bit about science communication. So you know what to do. Stick around. We're back at it. Segment 3, finally. Skylar's about had it with me. I get it.
No, it's been great.
It's been a very interesting and fruitful conversation, even outside of the recording time. So we'll just start right into it. So Skylar, you've been doing some research on education. Do you mind talking to me about that? What's going on? What are you getting yourself into?
So one of the reasons that I decided to come to ASU for grad school is that they have, what you have to do is a secondary project. So you do your main research, which is that galactic evolution stuff for me, but then you have to do another project in the first few years in a unrelated field or subfield. And there happens to be an amazing professor here named Molly Simon who does astronomy education research. And education research is a little bit more, I don't want to say social science-y, but it's a lot more stats and survey related, a completely different type of research than I normally do. But I am really passionate about education. I love teaching. I love talking about science, if you can't tell. And the idea of doing it more in a research format and understanding more about how people learn and what's beneficial was really interesting. So the specific project that I'm doing is through this program that is called Online Undergraduate Research Experiences. So ASU has a really huge online education program and a ton of different degrees offered. But one of the big challenges with getting an online education in specifically STEM fields is research experiences are really crucial if you want to go on to grad school or really a career in the sciences. And it's really hard to find those when you're an online student. So they've just started beginning these research experiences, and they're in a whole bunch of different fields. And so my research is kind of to study the effectiveness of these programs, and specifically working with qualitative data. So interviewing students, seeing what they thought of the programs, what worked, what didn't, and then doing qualitative data analysis to see what the trends are, what's working, what's not, so we can, kind of refine this program. And I think it's super fascinating because it's just a completely different type of research than anything I've ever done. And I think it's super important because, like, making science more accessible is a really big thing for me. I think that as a field, it has been very historically closed off, and especially for women and minorities, it is not seen as something that is easy to get into. And the types of students who do online education are typically people who are going back for a degree, or who have a family, or who can't come to in person for various reasons. And so those are the types of people who science might have been closed off to before. And it's really exciting to be part of something that is opening science up to a broader spectrum of people, because that's what makes science successful, is working with people from varying backgrounds and different ideas. So I think it's really exciting.
100%. It adds to the overall success of any project. Definitely.
Yeah,
just getting different minded people from different backgrounds. Absolutely.
Yeah.
Couldn't agree more on that. Second thing I want to say is that not only is it tough for women and minorities to get into STEM fields, but just freaking stay in STEM fields, after college. It's just
there's huge drop-offs in between senior year of high school and first year of college for women in STEM, and then another one after graduating college. We see these drops.
Yeah, and I think one metric that really stands out is just seeing people that are like you that are in higher positions, because it's almost I can do that. It's just a subconscious, I can achieve that. And I'm going to strive for it,
Oh, for sure. I think that's one of the most important things. My first ever research experience was at a pharmaceutical lab, and none of the senior scientists were women. I had another research experience at a national lab, and I was one of 2 women in a 20-person research group, and the other one had just started the year before. She was a young scientist. And the effects that has on someone is kind of hard to understand unless you're in that position. But there's this kind of sense of inferiority. The imposter syndrome really builds because you're often the only one who looks like you in a room. It's should I be in this room if I'm the only one who looks like this in the room? But I was so grateful because both of my undergraduate advisors were women, both in physics and astronomy, and they were just so understanding, and they knew the experiences, and they knew how hard you can be on yourself if you fail a midterm, but they could understand that, I think, in ways that someone who's not similarly minded or has a similar experience could. And it was a huge reason why I stuck with astrophysics, was okay, they did this, I can see myself in them, I can do this. And I think getting more women and minorities in upper level STEM positions or kind of administrative positions in schools is really important.
Definitely. Yeah, I couldn't agree more. We had a whole episode just talking about women in STEM. It was a fun episode.
Yeah.
I can't tell you how many times I've reached out to guests and then be let's talk about women in STEM. I'm we already did it. Okay, sure.
Yeah, sorry. It is very easy for me to go on that tangent, but I think it's an important tangent.
Well, it's applicable in every case, pretty much. It's statistically applicable. It's really unfortunate, but it's just, that's the facts.
Yeah.
So I do have a quick question about the research. So you're looking at how it could be applicable to the individual for their success in education. So do you kind of like sit down and have a conversation with them on, not really on what, like, because there's the notion that it's really preference on how you learn, not like how you're intelligent, because like,
Right.
right, because there's multimodal ways of learning, but like
Right.
some people just prefer visual versus
Right.
written versus, you know, etc. And you know, that's on an individual level. That's why it's really hard, I guess, in the first place for online, you know, education, is because not everybody can do it based on their own
Learning.
upbringing,
Yeah.
influences, unconscious bias, etc. Like it's a tough metric. So how
Right.
do you go about that?
So part of it is, you know, the people that I'm talking to, they aren't in traditional classes. These are research experiences. So they're either courses that are
Mm,
like designed as a full course to walk you through the whole research process and like do research and write it up, or they're like 2 week long like specialty programs to, you know, work on one specific research question or learn a specific skill. And so I think that that lends itself to a lot more independence in the work that you're doing. At least pretty much everyone I talked to, there was a lot of independence in how they went about doing their project, which
oh,
is really helpful for what you're talking about, the fact that
mhm,
everyone kind of works differently.
mhm,
And so I think that was kind of a big thing that I was learning about when
mm,
talking to people. Like, okay, like the independence here is important. And for a lot of people, doing research experience in undergrad is the first time that you are given any sort of trust or independence to do work on your own. And I think that that's really important for like developing your confidence in yourself as a scientist.
mhm.
Like another reason why I think these online programs are really great.
Oh, definitely. And
Yeah.
hopefully, there's a huge emphasis on the communication aspect,
Yes.
especially, you know, because I don't know how well this stands, but like as you continue to go into your master's and PhD track, you become more niche and less communicative. I don't know, you know,
It's a
so
big problem in science, in my opinion. Like, well,
yeah.
it's this thing. When you learn something, you go from unconscious ignorance, you don't know what you don't know, conscious ignorance, you become aware of the gaps you're missing,
Mhm,
conscious knowledge, and then unconscious knowledge. And most people who are in upper level degree programs or professors are pretty solidly in that unconscious knowledge phase. And
mhm,
so they're terrible teachers and communicators because they're like,
mhm,
well, I just know this. Like, why don't you know this?
mhm,
Um, and so something that I'm like actively trying to do in this process is practice bringing myself back to that conscious knowledge, like remembering how I learned something, talking to people who don't know the thing so I can understand their gaps in knowledge. And
mhm.
because there's no way I would know those gaps, but like being aware of the knowledge that you have, I think is a big thing.
Absolutely. And there's another big like point. There's another point here that I want to make, is that, and this is kind of funny because I was talking to, for some reason, every time I'm on an airplane, I sit beside somebody that works in STEM. It's hilarious.
That's amazing.
Yeah. Yeah. So the last two plane rides I had, I was sitting beside a dietitian, and then I was also sitting beside someone who worked or who runs their own company but has like a master's in physics.
Oh, cool.
And both people made really good points. We were talking about social media and the fact that there is a lack thereof whenever you get into higher education for communication, that it's giving way for the lay people to have a platform to talk about what you do without consulting, you know, like actual experts in that field,
Mm,
right? A good case in point, and I'm sure I'm gonna get some hate in this. I hate for saying this, but like the dietitian and I both agreed that like people like that are following these extreme diets, like
mm.
the Liver King, if you know
Yeah,
about
I
this dude
do
on
know the
TikTok.
Liver King.
Yeah.
Yeah,
This guy, like, he is doing extreme diets because he can. And people want dieting advice. There's not a lot of dietitians that are on TikTok making content on what you should be doing, which is a
right.
balanced diet. a sustainably sourced balanced diet. But because there's a lack thereof of that platform, it gives people the ability to make their own platform and use, how do I want to say, clickbait or outlandish ideas to gain an audience. And it's just not good. Like, and that goes for any sciences, like across the board. That's just an example.
Definitely a increase in misinformation because of social media platforms. Yeah. But I think it's been really interesting because at least the side of TikTok I'm on, and what's funny is any app like this, the algorithm can show you very different things. But I follow hundreds of scientists who are talking about science, who are qualified, have multiple degrees. And I think that their content is often so much more clearly knowledgeable that people tend to gravitate towards it a bit more and be like, oh, this person knows what they're talking about. I think there's this rise of the light side to counterbalance the darkness of misinformation.
Yes, the Sith can't stay in power forever.
Exactly.
I agree. Like there's definitely a shift because it's nuts. And one of the things that really showed me the misinformation magnitude was through the pandemic. And that's where I was like, holy shit, I need to start doing some science communication.
Dangerous.
Yeah. So that's why I'm doing what I'm doing. I could have done it like just physics and engineering, but I decided to go broad and also, you know, for my I guess being more well-rounded and talking to different people. But yeah, that's what I'm trying to do is get more, you know, information that makes sense out there and that's validated rather than just having these people have different platforms that spread misinformation.
Right. That's very important.
Yeah. So I was talking to someone, I'll let them be anonymous, but I was talking to somebody that has a lot of followers on TikTok. And one thing that they brought up was that they're trying to put together these groups to communicate with like TikTok, Instagram, Facebook, Twitter, etc., all these social platforms on how they can change the algorithm so that less misinformation is being rewarded by likes, comments, and views. Right. And yeah, so like obviously keeping like for again the Liver King for an example, keeping his already established community, but like making it harder for say like if he came out and said that like eating lettuce is bullshit, you know, like then that wouldn't be, the algorithm wouldn't allow that to continue to spread to like millions of people, so they have a shift in idea. I don't know, what do you think about that?
Yeah, I think it's an interesting line because there's such a lack of transparency in how any social media algorithm works, really, but I think TikTok is especially notorious for it, because I think part of the problem is the platforms don't always necessarily care. It's all about the interaction and how many people are using the app and how many people are liking and commenting. And so my kind of pessimistic outlook would be, it seems unlikely that that would ever change, really, to be honest. I think part of that, though, is also my feeling that, like, I am very new to social media. I am new to science communication and TikTok, and I feel very insignificant against the face of the algorithm and this powerful corporation. And I wonder when you have more followers, that changes because you have more of a platform and more of a power to stand up against it. So, you know, that might change, but, you know, my current approach is just share science and the things I'm excited about and put as accurate information as I know of out there.
Couldn't agree more. That's my approach as well. Obviously I ain't even close to what you are. Working on it. I ain't even close.
I don't know how I got here. It's truly a mystery why so many people like to hear me talk about science, but
it's entertaining and good quality content. That's it.
Thank you. Yeah. I think it's the dad jokes that really brought a lot of people in. Have you?
I have.
Yeah.
They're great. But you do like mine's more like, how do I want to say it? Like I don't do as much entertainment. Mine's more
Yeah.
like posing interesting questions, like the one time I was like, what is nothing? Let's talk about it.
Right.
Yeah,
Right.
and then just explaining what nothing actually means. When you say nothing, you don't really mean nothing.
Right. Yeah.
Or just, I don't know, like how we see everything in the past and based on predictions from like our compiled memory of
Mm.
what usually happens in a circumstance. Just stuff like that. I saw that you did a video. I don't know if you did it before me. It might have been like that, but where we see like, is it 0.0035
Oh yeah, a
percent
tiny
of the,
percent of light.
yeah, it's very tiny. Like I
Yeah.
try to do stuff like that. I don't really do like the jokes and stuff. So you
Yeah.
definitely
Well,
got the entertainment sector down.
for me, it started as just a creative outlet. Like
Yeah.
I was struggling in my second semester of grad school. I was struggling to motivate, figure out why this research was still fun for me. And then, I always loved TAing and teaching. And I was like, I might as well make videos because it makes me happy to explain things. And then I would talk about, oh my gosh, grad school is such a pain, or really bad day for imposter syndrome over here. And so I think because it started out not necessarily as explicitly science communication for me, but just as a creative outlet,
Mhm.
my channel has a pretty big variety of content. And I'm always planning on keeping it that way. Like I make whatever videos I think of and enjoy making. So sometimes that is dad jokes. Yep.
I love it. I
Yep.
love it. Well, is there any advice that you want to give for people who are trying to do what we do in terms of science communication, or just in general with anything that we've talked about today? That we talked about a lot. So,
Yeah. I mean, there's, man, okay. It's funny, I don't feel qualified at all for science communication advice, but I guess I kind of am. I think a big part of it is just staying true to the type of content you want to make, especially on a platform like TikTok. It's very easy to get caught up in, like when I first started, I saw all of these accounts that are like, use this trending sound and say this, and you'll get thousands of followers. And it's very easy to be like, oh, I think I have to do that or behave a certain way to get noticed. And I think that that's definitely not true. um, I also think that there's an element of trying to not do it for gaining a following, but for gaining the right following.
yeah.
Because a lot of times on TikTok, a video will blow up. You'll get, 100,000 followers from that one video who have never seen any of your other content. And then TikTok tries to pigeonhole you into making that type of content. So
Mm,
sometimes a slow and steady growth is much more valuable in terms of actually gaining the right audience who likes all of the different types of content that you make. And I think that's something that is often lost on people. And it's true of any platform, YouTube, Twitter. Sometimes one viral thing getting you a bunch of followers isn't going to be the best thing for a community you're trying to develop.
definitely.
I got tons of advice in terms of like being a scientist or an astrophysicist. Just try to do research experience. Imposter syndrome will show up, but it shows up for everybody. And I think that's important to remember. Um, remember what you like about a field. I always have a pretty space picture as my background so that when I'm ready to punch my computer because my code's not working, I'm like, okay, pretty space picture. That's why I'm here. Um,
Definitely.
yeah, I don't know. Is there anything else?
I think we're good. I mean, we've had a really fun, fruitful conversation about things that's being worked on, things that we really don't know.
Yeah.
Talked about some core science, things that I guess may make sense to us, but not to everybody.
Right.
I hope that if anybody's watching or listening to this, that they've learned something, at least based on how the science is approached.
Yeah.
Yeah.
I hope so too.
Yes. Yes. But hey, Skylar, this has been great. I've had a lot of fun. It's great getting to meet you. This is the first
Yeah.
time we've met.
I know.
So it's been wonderful. Thank you for being on the podcast.
Thank you so much, Sam. I have had a blast.
Awesome. Well, ciao.
Bye.
That is all for this episode of Everything STEAM. Now let me give a big shout out to Skylar for taking time to share some expertise in some really niche sectors like galactic evolution and dark matter. If you love science, astrophysics, and dad jokes or just really cool content, I recommend you give Skylar a follow like I did on TikTok, YouTube, and Twitter. The links to do so will be in the description or on our website, everythingsteam.org. I would also love to mention my amazing team for their collective efforts to make this show happen. This podcast was edited by Ariel Piermont, marketed by Courtney Page, QC'd by Panupit Erikset, and our episode art was manifested by Gabrielle Edmiston. After the episode, please give our podcast a rating and review on whatever platform you get your podcasts on. We're always looking for feedback, and the rating would greatly help us out in the fight against the algorithms. Lastly, be sure to check us out on all the socials for podcast news, upcoming episodes, and just fun STEAM content. Just search Everything STEAM on Instagram, TikTok, Facebook, and Reddit to join in on the fun. Once again, thank you for listening to Everything STEAM. I'm your host, Sam Stanford, and as always, stay curious.